given a ordinary linear differential equation f of d y is equal to f of x. We have seen how to solve when f of x equal to 0, right? That is f of dy is equal to 0. This we have already seen. Now we look at situations when f of dy is not equal to 0. That is f of x is not equal to 0. So let's look at the relationship between the solutions when f of x is equal to 0 and when f of x is not equal to 0. So to begin with, let's say y is equal to u is a particular function of f of d y is equal to f of x. So which implies f of d u is equal to f of x. Now what we'll do is we will do something like this. We'll say f of d of u plus v is equal to f of x. Now this can be written as f of d u plus f of d v is equal to f of x. One of the rules. Okay. Now this and this can both be true. Both can be true at the same time only if f of dv is equal to 0. Yes. Now this is again a ordinary linear differential equation with RHS equal to 0, right? And we know, which means the solution would be, let's say v is equal to f of x containing n arbitrary constants, in which case the general solution of f of dy is equal to f of x would be, remember we have seen this, right? So we add up these, so it will become y is equal to u plus f of x. Now here this is called the particular integral and this is called the complementary function. Therefore the general solution would be the sum of particular integral and complementary function. We know how to find the complementary function, that is when RHS is equal to 0. Again we have seen three cases in case of this: when roots are distinct and real, when roots are repeated, when roots have conjugate pairs of complex numbers. Now we have to figure out the particular integral. Okay, so to figure out the particular integral, let 1 by f of d of f of x be some function which, when operated by f of d, gives f of x. Okay, so therefore 1 by f of d f of x is a particular function, particular integral of f of d y is equal to f of x. Now y is equal to 1 by f of d of f of x means f of dy is equal to f of x is satisfied. Basically what that means is, if we substitute y back, we get f of d. Yes, so here this 1 by f of d is the inverse operator of f of d. Remember, f of d is here the derivative, d by dx. Yes, so 1 by d would be the integral, that is this. So all this, what it implies is that 1 by d f of x is equal to integral of f of x dx. Yes, so here this part 1 by f of d f of x is called the particular integral. Now in case you end up with 1 by d to the power of n, I'm saying d to the power of n, but here we are talking of the nth time, right? So if we just say dn, then we are talking of nth derivative, right? So let me put it this way: if it is dn, then nth derivative. If it is 1 by d to the dn, then it is the nth integration, or integration done n times. And here, in case of particular integral, no constant of integration required. Okay, so remember here the key thing is that if you have a function equal to not 0 but something else, then in that case you have to figure out complementary function, figure out particular integral, and the solution would be CF plus PI. Now in the next session we will look at it in more detail. Bye for now.